Telescope, instrumentation, and discoveries. On behalf of IAPT, Indian Association of Physics Teachers, my warm welcome to you, Dr. Divakar Mayya. I also welcome all office bearers, students, teachers from various research and scientists from various research institutes, and also all the people who are logged into this, all the participants. My warm welcome. Now I request Professor Bole sir to introduce about IAPT activities to the audience. Bole sir.
Good morning all. IAPT is the Indian Association for Physics Teachers, as you all know, was established in 1980 with the aim of upgrading the quality of physics teaching and physics teachers at all levels. More than 10,000 life members are there, including approximately 100 from out of India. All IAPT work is voluntary. IAPT mainly conducts every year national standard examination in various science subjects, for which every year about 2.5 lakh students appear, and they are selected to national and international Olympiads through these examinations. It also conducts summer schools, competitions, workshops, training programs, a lecture series, and so on. It is every year there are competitions on essay writing, innovative experiment competition is also there, and it is open to students of junior college, degree college, as well as the teachers at various levels, including the research students also. So in general, for the upgradement of physics education, the IAPT is striving hard. As I mentioned, the work is voluntary, but we could get good people as the members, including the scientists and the members of atomic energy commissions and so on, and that is why the establishment is able to can do a better work in all over India. Today, we have our MD series third lecture. Dharkar was one of the fellow who have dedicated his life almost after the retirement to IAPT, and single-handedly he handled the examination work and established a model to which the examination now can be conducted throughout India on the same day, at the same time, and with 2,500 lakh students appearing for the examination. So these are the this type of people, including the Dr. Khandelwal as well as the Professor Saraf, and so many people are there who are working for the upliftment of physics teaching in India. With this brief introduction, I will hand over the mic to Hema.
Thank you, Bole sir. I'm very happy to say that today we have with us Professor Bhupati Chakrabarti. He was General Secretary of IAPT at national level, and he associated, he's working on physics Olympiads. He's associated with HBC SC, and he worked with Professor Dharkar for many years. So I'm very sure that he has many fond memories of Professor Dharkar. So I request you to share some memories with us. Sir.
Thank you, Madam. Namaskar and good morning to everybody. This is, in a way, an honor, I must say, to speak before such an excellent gathering on Professor Dharkar. And I'm also very happy that I must thank my IAPT colleagues from Mumbai that they have taken such an excellent initiative. So for Professor Dharkar is concerned, if I'm allowed to sum up about him from my perspective, I can say that he was my guardian in IAPT. In fact, I first came to know some 25 years back when I joined IAPT some 2-3 years back only. Before that, in 1997, when IAPT convention was held in Midnapur town, in Midnapur College, on the occasion of 125th year celebration of that college. Midnapur is a district town in West Bengal, located 130 kilometers from Kolkata. At that time, everyone used to travel by train, mostly by sleeper class. Professor Dharkar also arrived there. But by that time, he, of course, has retired. And if I remember correctly, he retired in 1996. And I had a first and brief interaction with him. But soon, he really entrusted me with certain responsibilities. Some of you might be knowing that at that time, this NACP examination, those were really being evaluated. There was no machine marking. Those were evaluated those with some stencil, and the answers were being, model answers were being sent. You will have to put up the transparent sheet over the answer script, and you will have to find out the number of correct answers. So he entrusted me with the responsibility, and I immediately started working. But gradually, I could feel that he is a person in IIPT with whom you can talk frankly, although there was a difference of age. And particularly, if I'm allowed to use this particular comparison, I should say, since I believe I also worked all throughout my life in an undergraduate college, he also had the same background. So possibly he could understand my language better. So that way, I appreciate his inclination for doing good experiments and suggesting nice experiments, particularly for the NGP Part C. And some of you might be knowing, in 2001, for the first time, when S.N. Bose National Center for the Basic Sciences showed their interest in inducting the NGP top 25 students directly for their interview in the integrated PhD program, the students, really all the students, came down to Ramakrishna Mission Belu Vidya Mandir, where we had this NGP exam along with a workshop, and then they went straight away to S.N. Bose Center. And I still remember 2 of the students joined there, and they have done very well later on. That was an initiative could only be possible because of Professor Dharkar, because at that time he was working as the chief coordinator of IIPT exam. And gradually, we also learned how to make good questions for IIPT exams, not only for NGP Part C practical, but also for the NSCP and other examinations. And the most important thing I must admit, that Professor Dharkar was so approachable. He could understand the things in a nice way. And so I gradually got more and more involved in IIPT activities. Definitely, as it happens when you want to do certain work, there are difficulties do come in the way, and you need to really look for certain solutions. But if you get advice from a person of the stature of Professor Dharkar and with his stupendous experience, you really gain a lot. That's exactly what happened with me. And I always talk to him on so many issues, innumerable issues, I must say. And I've always got good advice. He has criticized my thought process. He has given me good suggestions. He has appreciated certain points. He was so frank and so nice. I always had a great support in IIPT. And particularly, as it has been mentioned, I was a general secretary for 2 terms, starting from 2013. I got huge support from Professor Dharkar, and I must mention that all of you know I got a wonderful president to work with in the form of Professor H.C. Pradhan. Professor Pradhan was a wonderful president to work with. He was, always giving such nice suggestions, but he is leaving the things to me that, well, this is the thing, you try it, you do it. He never tried to impose anything. And one of the suggestions was that, well, if you have any difficulty, you must talk to Professor Dharkar and some other persons like Professor Oglapurkar and others. So I have a lot of memories, because this NGP Part C exam, tying up with the workshop that we are holding, still we are holding it, and it is now named after the memory of Professor C.K. Mojumdar. It's a flagship program of this region of IIPT RC15. We are still working on it. On several years, we have really done this workshop as an all-India event, where all the students who have been qualified for the practical exam in NGP Part C, they have come, attended the workshop, and then they have done these experiments. And I must tell you, some years back, Professor Dharkar really handed me over a good collection of his old experiments and the question papers on these experiments, and I found that is very interesting. I mean, that's interesting from the historical point of view. If you really go back to the questions of NGP Part C said in the say, 90s, late 90s, maybe the early 2000s, you will find that those are rudimentary at this point of time. But if you consider the equipment available, the laboratory training the students used to have at that time, those are perfectly all right. Those are very good assessment tools for the students. So Professor Dharkar has worked in, if you really look at it, he has taken the responsibility of the chief coordinator of examination. For a long time, of course, he has worked. He has really, not like me, he has really mentored so many people, and he has brought in so many people in the IPT activities. I'm really, surprised to see his astonishing capability. Now, and with all this all these things said, all of us know what a wonderful person he was. So approachable, so nice, and he could understand the issues people are having. Not only for me, he has helped by academically helped a lot of people by providing excellent suggestions. So, if I really go on talking about him, possibly it'll be endless. But I feel that I've lost my guardian insofar IPT is concerned, because whenever I used to look back to him or just used to approach him with any issue, he used to come up with nice suggestions. I must say that he always didn't agree with me, but his disagreement was logical. That's why I used to appreciate his points of view. That way, I know not only me, it was a personal loss when he passed away 2 years back, but I also know it was a big loss for IIPT. It's very difficult to get a person like Professor Dharkar, and I appreciate my colleagues in Mumbai, IIPT colleagues in Mumbai, that they have taken this initiative in the memory of Professor Dharkar for this lecture series, because he is a person, he is a teacher who could motivate not only people like us, but even much younger people. They could be motivated by his very interesting and magnetic personality, I should say. So I once again appreciate this initiative from Mumbai IPT Sabarsi, and I feel that this is a suggestion. Possibly we can think in IPT in a broader scale. We can think about certain doable programs, not very lofty things, certain doable programs in the memory of Professor Dharkar, maybe at the all India level, or even different artists can emulate this thing, what is being done by Mumbai Savarsi. So I once again thank all of you, particularly Professor Kamla Bodde, Professor Rekha Ghodpade, for providing me this opportunity to speak before this gathering from the bottom of my heart about my association with Professor Dharkar. But as I've told you, there are lots of things we can talk about. We go on talking, it's nearly endless, but I will have to stop in any way. And I once again wish this particular lecture series goes on in a nice way, and we shall be able to join again here, maybe with some other, listening from some other IPT colleague about Professor Dharkar and his experience of interaction with the Professor Dharkar. So with this, let me stop here. Thank you. Thank you very much. Namaskar.
Thank you, sir. Now I call upon Sushmita Mehta to introduce the speaker to the audience. An announcement. If there are any questions, please put them in the chat box. The speaker will take the questions after the talk. Sushmita.
Thank you, Hema ma'am. Dr. Professor Divakar Mayya today is our guest, and we would like to welcome him. Let me introduce his big things that he has achieved in his life. He is an astrophysics at the National Institute of Astrophysics, Optics and Electronics, INAOE, Puebla, Mexico. He is a professor and a senior researcher in astrophysics at the National Institute of Astrophysics, Optics and Electronics. He has done his PhD from the Indian Institute of Science, Bangalore, India in 1993, and his topic was star formation in giant exagalactic H2 regions. He was a postdoc at TIFR, Mumbai. He had been in the editorial board of Journal of Astrophysics and Astronomy, co-published by the Indian Academy of Sciences and Astronomical Survey of India. For more than 35 years of research experience and 25 years of teaching at the postgraduate level, his specialized topics have been star formation, star clusters, and galaxies. His experiencing in using the HST and JWST data and other international ground-based facilities, such as the largest optical telescope, that is about 10.4 meter GTC, that is Grand Telescopia de Canaries. Experience has so much to tell about Divakar Mayya. He has around 80 research papers in peer-reviewed journals. It is indeed an honor to have him over here to give us a little talk. Directed around 25 PhD, MSc, and BSc journals. He has guided the students, about 25 PhD students. His vast experience in outreach of astrophysical topics. He is a life member of the International Astronomical Union and Astronomical Society of India and Mexican Academy of Sciences. We are indeed fortunate to hear from him. Thank you. Kindly guide us in this region. Thank you. Thank you, sir, for coming.
No, thank you, Sushmita, for a nice introduction. So thank you all for being connected to hear this talk. And if everything's okay, I can start sharing, right?
Sir?
Yes.
Hello, sir. Sir, would you like to get questions when you are talking or towards the end?
Limited questions is, it's okay asking questions in the middle. I don't have any problem.
Okay.
Yes.
Otherwise, we'll ask them to put their questions in the comment box, and then towards the end, we'll discuss all the questions. Would that be fine?
Yeah. Even in the middle, it's okay. I don't have any problem. If it's too much interruption, I will see. But it's perfectly, it's okay.
Okay.
No
Thank
problem.
you, sir. Thank you.
Okay. Yeah. Shall I share the screen?
Yes, sir.
Yeah, tell me when you see the slide.
Yes, sir, it is very clear.
Okay?
Yeah.
Sure. Okay, then I will start my talk, which will be, as already mentioned, on the James Webb Space Telescope, which I will focus on the instrumentation and the discoveries that this telescope has made in its short lifetime of now 5 months. So, as some of you may be aware of, this telescope was launched on the Christmas Day last year, and for the next few months, the telescope was being tested, and And on 12th of July, the first scientific results were dedicated to the world by the American president, Biden. So that from that day, we know we have images, or we as astronomers have access to the data from this telescope. So in this short period of 5 months, the telescope has already produced very interesting results, and also have excited the several astronomers and in general the entire astronomical community. So I hope I can share this excitement with you. In fact, I'm just back yesterday, actually, around this time, back here in Mexico after attending a conference to celebrate or to know the results obtained from this telescope. So I will include whatever experience or whatever I heard over the last 1 week there in this present talk. Okay, so there's some background noise. I think you have to mute you. Someone there.
Everyone else except the speaker is requested to get muted, please.
Yes, Emma Singh, you'll have to mute it.
Suddenly it started. Yeah. Good. So it's really a pleasure for me to give this talk to the teachers, because teachers are the one who finally enlighten the students. So yeah, that way, whatever I give today, whatever I hear, it will be transmitted to many more people. So that is my wish, and that's why I'm happy that I'm giving it to teachers, so that teachers will transmit to other people. And finally, these younger generation, especially in the BSc, so they are the ones who will continue the research or whatever top investigation in the scientific fields, not necessarily in astronomy, but in general the other scientific fields. So astronomy always has been a driver for physics and other fields. So it's good that we use astronomy as a motivating factor to take any other field in science. So before I start, let me put you in the context of where we are in modern astrophysics. That's why this slide. Just rapidly, I go through that. So let me make it clear that astrophysics is an observationally driven science. You know? So when I took the courses, it was more than 35 years ago in IAC. So, for example, the idea was more, the courses were more theoretically driven. You know? Especially in the cosmology, it's completely theoretically driven. So, but present astronomy is very different. Present day, especially the courses, we are driven by what is observed in the universe, and only those theories which are explaining the phenomena are considered as valid theory. Otherwise, rest of the theories are just mathematical possibilities, but not applicable to astronomical objects. You know, so that's the general idea that these days we have about the astrophysics, and also the astrophysics is an observational based science, in the sense we can't carry out experiments. You know? So experiment, we can't bring our star into our homes or laboratories and do experiments with that, like changing the temperature or densities. No, we can't do that. So, but we have other ways of doing that. So what we do is to collect large samples, and from there we group them into, let's say, if it's a stellar sample, we group them into stars of similar temperature and study any property that we want to study as a function of temperature, for example. So that's why we do a lot of statistical analysis, and for some topics, so we may study some individual objects to make things very clearer. So since we depend, since we analyze large samples, so we should make sure that the samples are not biased. No, so that's why we carry out a lot of numerical simulations to make sure that our sample selection is correct, and also the capabilities of the instruments may change. So we should exactly know what is the capability of the instruments. So all these things can be simulated first, and those simulation data results will be compared to the observations. No? So that's another way how astronomy is carried out today. And one of the very important thing is the multi-band observations. The olden days, optical astronomy was the leading astronomy. Well, these days also, optical gives us a lot of information, but always it is complemented by multi-wavelength observations, because finally the radiation that comes is electromagnetic radiation, and that is distributed over the entire frequencies, right from the low radio frequency to the X-rays and gamma rays. So we need to understand any astrophysical phenomena over the entire band of electromagnetic radiation, so that we can say that we understand that object. So another recent trend over the last 2 decades especially is the collaborative projects. So hardly we see now individual persons carrying out a project. No, these days the kind of work we do is in collaboration. That is, some people, maybe friends or collaborators, invite collaborations from another group just to think about how we solve a particular problem. So we look for experts in other fields, and to make we take ideas so that how we can really understand the phenomena, and hence the group always grows and grows. So finally it can become a large group. And the advantage of being a large group, that then there are no real barriers. We can really get into the bottom of the problem until it is solved. So for some very successful such projects are, one of them is Event Horizon Telescope, which a couple of years ago produced the first image of the shadow of a black hole, for example, where a telescope from my institute also had participated in this project, for example, and it was a telescope combining telescopes that are there everywhere in the world, in at radio frequencies, for example. So another example is the gravitational detection, also required collaboration from researchers all over the world. No? So another aspect of current day research is the amount of data that are available in archives. No? Because once you get the data and it is documented, and data is just left so that anybody else can be used. No? In fact, these days, there is so much of data that has not been used, but it is in the archive. So anybody can do that. So why I'm telling that, because for example, in universities, most often we have teachers who think that they don't have facilities to do astronomy, but these days that is not a barrier at all, because there's so much of very good quality, almost unused astronomical data just sitting there. We need just an idea and experience to work on that. So all these things make these days anybody can work on this data. No? So you don't need to have a telescope. You don't need to have access to big computer. So you can do it using your personal computer, just downloading the data, following the instruction. No? So that's just a very brief way how we astronomers work today. No? So I continue. If there is interruption, please let me know. Okay. So let me also just give an introduction of what we consider the frontier topics of modern day astrophysics. So, for example, the formation of the first galaxies is what we want to learn, and also we want to learn how did the universe form the majority of its stars? When did it form? So another topic of interest is we know that every galaxy has a massive black hole, and then we don't know when exactly they were there in the galaxy, right from the beginning or somewhere they got formed. So, but it seems like black hole grows as the galaxy grows. So we want to understand how this co-evolution happens, for example. Another topic is the nature of dark matter and dark energy. So still there are enigmas, and at least in the near future don't see a solution, at least from the astrophysical point of view. Maybe the particle physics and other branches of physics may contribute there. So, and another very popular topic of research these days is the search for habitable planets. So, is there any habitable planet nearby? How close it is? So, as an astrophysicist on formation of stars and all, I mean this is interesting for the public, but here. Most of the physics that is required for this topic is well known, and this topic deals most with the chemistry and biology applied to the astrophysical objects. So I'll be talking about James Webb Telescope, and James Webb Telescope will be able to contribute to all these topics except the nature of the dark energy and dark matter. So that's so I will show some of the images, some of the results obtained in these fields today. Okay, so usually whenever we talk, like in astronomy, any field, it's easier to talk about our wish list, what we want to do. But I would like to take this opportunity to also talk to you about what results we already got. So it's amazing. In the last 3 years, we have really solved some of the long-standing problems. One of them, for example, is the answer to the question of how old is the universe. Actually, when I did the coursework, when I entered the astronomy, the age of the universe were anywhere between 10 and 20 giga years or billion years. So we didn't know how much, but these days the precise number has been put into that 13.7 giga years. So, and that is related to the Hubble constant, whose value also was fluctuating between 50 and 100 around 30 years ago, but in the last 3 decades, its value is fixed at 72 kilometer per second, with an error of as small as like 3 kilometer per second, is like less than 5% of error. And it is mainly thanks to the Hubble Space Telescope, which was launched in the 90s, and that its main intention was to obtain this Hubble constant, which it did very successfully. And another topic over which we know, quite good today is the stellar evolution. There are still some aspects of evolution of massive stars where we are looking for some details, but in general, we know exactly the time scale over which stars evolve. So same way, another topic is the star formation. So we now understand the star formation. We know what are the final blocks of star forming clouds. And this is basically another NASA telescope, the Spitzer Space Telescope, contributed enormously over the last 2 decades in this field, so that we know exactly how stars form and in what range stellar masses can be. All these things we know, especially these days. There is an ALMA telescope. It's a millimeter, it detects millimeter waves. It is in Chile. So this ALMA telescope is also very powerful to look at star-forming regions. This graph here shows how the Hubble constant progressed. Hubble constant, its value was obtained over the last 2 decades. So right from the Hubble discovered its value, which was around 71 kilometer per second, there were several other missions. So all other missions obtained the values within the errors of the Hubble. Hubble had a larger error, and all these other missions over the years managed to put a lesser error bar basically, but the value is around the same value as Hubble has obtained around 20 years ago. Okay, I'll proceed now to the recent results from the James Webb Space Telescope. I'll start with the galaxies and then talk about the nebular objects and finally on the planetary systems. Well, galaxies are all the objects. Our Milky Way is our host galaxy, and that there are several galaxies like Andromeda in our neighborhood, and all these nearby galaxies we call matured galaxies. So in this plot, they are on the left side. So or their distances, we can say it's almost to zero because they are local galaxies. I'm talking here about a large distance scale. So we know that Andromeda is around 2 million miles, 2 million kilometers away, but the distance scale that I have put here, it's almost like local and zero. No? So as we go to the right in this diagram, so we are seeing objects whose light left those objects many millions of years ago, no? Actually thousands of millions ago. So such a way that, for example, another unit of distance which is frequently used by us is called redshift. So larger the value, the object is at a greater distance. No? For example, at a redshift of 1, so all the objects which are nearer than redshift of 1, they are formed, let's say, in the later half of the lifetime of the universe. No? Whereas all the objects between 1 and any value that is higher than that, so those objects are formed in the first half of the life of the universe, or in the early universe, let's say. No? So the question is, where is that beginning? No, beginning probably you heard of the Big Bang. I won't be talking about the Big Bang, but the Big Bang is where everything started, and we believe that happened at 13.7 billion years. So, and the redshift corresponding to the Big Bang, it will go to the infinity, but that first few million years will start getting some values, and we don't know what is the highest value of this redshift in the observable universe. No? So that has been a challenge to get every time objects of higher and higher redshift. No? So this value, in recent years, if we discover a galaxy at a redshift of 4, we were happy. Oh, it's a very high redshift object. But over the years, that limit has been pushed, especially the Hubble. This plot shows how that limit has been pushed ever since the Hubble Space Telescope was launched in the 90s. So that was pushed up to the 4 redshift of value of 4. And with the continued observation of Hubble over a same field, so made the sensitivity levels even higher, and that allowed us to reach redshift values of 7. You know? So, and even more deeper observations, which means even more exposure times with the Hubble telescopes, allowed us to discover objects even up to redshift of 10. You know? But the number of objects that were discovered were very, very few, and it made us believe that hardly there are any objects in the redshift more than around 4. Number of objects above 4 were discovered, but the number were very low. So that is like one of the questions I put: when did the majority of the star formation happen in the universe? So to answer this question, we didn't know when exactly the galaxies formed. So, and with the Hubble, we found that number of galaxies that are formed above redshift of 4 were every time less and less. So that's why now with the Hubble Space Telescope, just in 5 months, so that number have been pushed into values higher than 6. Now there are lots of galaxies in such a short period of time, lots of galaxies discovered above redshift of 6. So actually, Hubble Space Telescope, the James Webb Space Telescope was built to discover these high redshift galaxies. So, and it is delivering. That good news is delivering. So right now, the galaxy with the highest redshift is 13.2. So the redshift limit has been pushed up to 13.2, and it will only increase in the coming months and years. We hope. If it doesn't increase, then we can say that we have understood when exactly galaxies formed. So we know that this James Webb Space Telescope has the capability to detect even up to redshift of 20. So that means we are talking about galaxies that are formed just 200 million years after the Big Bang. It's such a small period of time, for example, and we don't know whether galaxies are formed over such a short period of time. So the James Webb Space Telescope will answer that question without doubt in a couple of years. Well, this is the first image that was dedicated to the world by the James Webb Space Telescope. So this is a map of a cluster of galaxies, and the cluster of galaxies is what you see in the center of this image in white color. Hopefully, you see my cursor. So, and otherwise, I'll be saying where exactly I'm talking about. So the center of the image, there are several white points. Actually, in this image, every point you see, most of the points you see are galaxies. The points which are not galaxies, or the stars, are those which have these spikes, which are diffraction spikes from the telescope. So that there are a few of such objects. So all the other fuzzy objects are all galaxies. And there was a special purpose why this field is taken centered around a cluster of galaxies. So this, I will come back to this image. So this is because the cluster of galaxies, one would think that it will block all the objects that are behind that. In fact, cluster is at a very low redshift, and the interest in putting the cluster in the middle of this image was not to study the cluster, but to use the cluster as a magnifying lens. So in fact, clusters serve as a magnifying lens, and this magnifying lens works in the following way. So if and this process is called gravitational lensing. So what happens is, if you have an object just behind another astronomical object, so our observers are here in the bottom. So we have a very massive cluster of galaxies in the front, and exactly behind that, if another object, what happens is that the rays of the light, as Einstein showed in his theory of relativity, even the light is bent when it passed through a gravitating body. So it happens that the light is bent, and light otherwise it would have gone to other places in the universe, but it comes to us, for example, following this path. So effectively, that increases the brightness of the object. So rather, it is like a magnifying lens. It magnifies the object. So the object would have been too faint to be detected if not for this magnifying lens. So that's why the object in the previous slide was put behind, the cluster of galaxies is centered, so that we can see all the objects that are exactly behind that. Instead of blocking, it is magnifying. That is the beauty of how these gravitational lenses work. Well, in this image, we see several arcs, red arcs. And all these red arcs are at an extremely large redshift behind this magnifying lens, and they are actually they are coming from different objects at different redshifts. So they are being farther means they will be fainter, just because of the inverse square law dilution. So, but because of the gravitational lens, so they got brighter, and we can detect it. So, well, they have red color here because they are at a greater distance, so their light is red shifted. Their light is moved to the redder wavelengths. So that's why the red color means it is moved into the redder wavelengths here. So this has allowed us to detect so many objects which otherwise would not have been detected without the lens. Well, this is an infrared image. Well, the Hubble Space Telescope works in the optical wavelengths. Basically, it is the same wavelength that our eye is sensible, only that detectors which are used for Hubble Space Telescope, like charge coupled devices or CCDs, so are sensitive to ultraviolet wavelength and some part of the near infrared. So whereas James Webb Telescope is completely designed to detect infrared waves. So one of the consequences of the redshift is that the optical light of high redshift objects get shifted into the infrared. So that's one of the reasons why the Hubble Space Telescope was not able to detect many galaxies that have redshift higher than 4, because all their light from the stars get shifted into the infrared, and that's why this James Webb Telescope was designed to operate at the infrared frequencies. So that's why here you're seeing all the arcs in the infrared. Actually, their rest frame light is all optical. So only that optical light is shifted into the infrared, and there we see these arcs. Okay, I will come to that image in a little while. So let me also show you this one magnificent or fantastic example of this gravitational lensing in this right image. Right image, you see a perfect ring, which is little yellowish, and in the center you have blue object. Actually, the center is the galaxy. That is the lens here. And it seems like exactly behind that there is another galaxy, exactly in the line of sight. So that Einstein proved that in this configuration, you will get a complete ring. Whatever structure you see in the ring, it is a structure of that object, whatever was there behind. So, so here we got a perfect ring. This is not a new discovery from the James Webb Telescope. It was known before. So, but James Webb took the images, and it showed that its emission can be seen even at mid-infrared wavelengths, around 10 microns, I'm telling. When I say near-infrared in the astronomical regime, we're talking about is between 1 and 5 micron, and mid-infrared for this James Webb Telescope between 5 to 30 micrometers. So that's the range of wavelengths where James Webb Telescope operates. Okay, so you have a perfect ring here, which is called the Einstein ring. Okay, so in the image that we saw, where the galaxy cluster is centered, so we saw a lot of arcs. So I will talk about the instrument itself later on. This James Webb Telescope, one of the beauties of this telescope is a number of instruments it carried with that. So it had instruments for all purposes, and it could immediately center on any of the arcs and take a spectra. So the spectra gives us information about the redshift. So if the images are beautiful, but they don't give all the information. We need really spectra which give us information about the chemical elements any object has, and analyzing the chemical elements, we can get the abundance of different elements. We can get also the redshift using the simple Doppler formula, relativistic Doppler formula. So that will give us the redshifts, and all these lines we see, we are very familiar in the optical spectra, but now we are seeing those lines in the infrared spectra. Actually, even ground-based telescopes do not have a spectrograph of which gives so good infrared spectra. No? So that is one of the reasons why we are so excited to see these spectra, which were so familiar, but only for nearby objects. Now we are getting this spectra for the object which is at 13.1 billion light years away. No? So one of the only 600 million years after the Big Bang, this object formed. So this is this tiny dot here, which was amplified, which is seen as a very red object here. So that is one of the one of the farthest objects in the universe here. So, well, how do we know? Because, for example, as I said, we do a lot of simulations. For example, this is a simulated spectra of a nearby galaxy like the Milky Way. But imagining that if we move the Milky Way to a distance of redshift 10, so how it will look? So it will look in infrared. There are no numbers here, just a qualitative graph telling that the infrared wavelengths it will move. If the redshift is 10, we'll see some of these markers, some of the emission lines, some of the transitions from the oxygen and hydrogen atoms. Characteristic of galaxies, especially the spiral galaxies like the Milky Way. So we can identify those features easily, and that way define its redshift. So now a redshift 10 object, we can get a spectra like that with the James Webb spectrographs. Whereas if the redshift is 11, it will be moved. You can see it has moved to the right, and redshift 12, it will move further to the right. So that's how we can identify, looking at the spectra easily, we can say what is its redshift. So here are the other examples. For example, redshift, you can see this 1, 2, 3, 4 objects which are not even seen in the full-scale image, but there are close-ups of those images where you can see the galaxies. So we see the galaxies at 11.3, 12.6, 13.0, and 13.1 billion light years. So each one, these spectra were, this colored image was prepared for the public, so that public can easily appreciate these lines, which are slightly technical to understand for the general public. Okay, so this is somewhat technical, so which is expressed in redshift itself. So this object at redshift of 13.2 is now the record holder. So it's another field, not the field that that I showed you. So there's another field where deep observations have been taken. So and its spectra are seen like this. No, the spectra are do not have very easily identifiable emission lines, but it has a characteristic jump here or to the left side where there's a red or yellow line is put, and that jump helps us to identify the redshift. More redder or more to the right is the jump, more is the redshift of this object. So that's why the object with the highest redshift is at the top with the redshift of 13.2. So then, for example, this is a very, very interesting case of an object that is that has been lensed 3 times in a single image. That is the same galaxy image I showed you earlier. So it has well, what happens is when there is a lensing system, same galaxy can be seen more than once, because probably there is more than one optical path to reach us. That's how the lens works. So then we can see the same object in 3 different places. So by carefully analyzing the spectrum, we will see the tops. It's a repeat spectrum. So it is the same object, and that's very interesting. In one of these objects, it had a supernova explosion, for example. So then we can predict when the supernova explosion happens in the other image, because we know they're coming from, like, we can predict the future in these images. Now we can say this particular galaxy is going to explode because we have already seen it in other image where the ray, the path length was shorter, let us say. So that is also have been seen, for example, in the James Webb images. Okay, this is another galaxy, Stephan's Quintet, which is a loose group of 5 galaxies, where we see the Hubble Space Telescope image to the right and the James Webb image to the left. And these galaxies are actually colliding with each other without interaction. They are there like that for more than 1 billion years, we know from previous observations. And that's a mystery of exactly they avoid colliding with each other and how they survive like that for so many, more than 1 billion years. So, and the James Webb clearly shows that there is some action, probably the star formation, going on in between these two galaxies here. No? So another object. So of my interest, for example, this is one of the galaxies that I studied using this James Webb data. So this is a very nearby galaxy. It's only at 30 million light years, which for us very nearby. So, and this galaxy is filled with holes, and popularly this is called a phantom galaxy. So it's a scary appearance, which is coming basically because of so many holes in this galaxy. And the holes are formed because of action from massive stars. No? The massive stars blow bubbles actually in the interstellar medium, and I got curious to know why such a big bubble is formed. This big bubble is really big. It is around 3,000 light years across, and it's too big a bubble to be formed because of simple stars. So I here showed that in fact that image has a cluster of stars inside sitting. You know? So there are many stars inside, around almost 1 million stars are there sitting inside. So these stars are responsible for blowing this bubble. You know? And more closely here in the large imaginary cloud, for example, a similar bubble is it's a very recently released image. So there is a well-known star cluster called Tarantula Nebula, and there is this star cluster in the center of that. So, and the James Webb, especially the mid-infrared images, there is a big bubble seen exactly like the one I found in NGC 628, the galaxy I analyzed. No? So this is some examples of extragalactic research on this. So I will move into the nebulae now. And I'll request someone to tell me when I have to stop, especially some 15 minutes before, so that I can hurry up. So I will give, or if you have questions, I can make a break here. I go ahead?
Yes, you can continue.
Okay. Okay, this is another spectacular image of the Carina Nebula. So this seems more spectacular when we compare this image with the image in Hubble Space Telescope. Actually, just note that it's a very photogenic nebula, and this wall or mountain-like thing basically is a large gas cloud. And we know that these gas clouds are where the star formation happens, or where the stars form. But usually the stars form inside the cloud, and the clouds are opaque, like here in the Earth also. When there is cloud, we can't even see the sun, and sun is so bright for us. You know? So that's why we can't see anything that is inside these clouds. If you use any telescope which works at the optical wavelengths. But here you can see that this cloud, the boundary is seen, but then in the cloud you see the colored stars. It's filled with colored stars, so which means we are penetrating the gas cloud. So we are seeing exactly the stars forming inside these clouds. So that is really remarkable in this image. And earlier we had these kind of pictures using the Space Telescope, but this telescope has around 50 times better sharpness as compared to the earlier images. No? So that's why we can see individual stars in this image. So this is the comparison with the Hubble Space Telescope image HST in the top, whereas the JWST image is in the bottom. We can see that this hardly any stars are seen in the inside the cloud, whereas as I mentioned, there are several such bright points in the cloud here. No, so this is basically because the clouds are transparent to infrared waves. Infrared waves, even when it's cloudy, so infrared waves pass through. Infrared radio waves pass through, so we can see. So here also the same way. In the optical, for example, this Carina Nebula, one part of the Carina Nebula, we don't see any stars, but in infrared, a zoom of the infrared image shows us many stars inside this cloud. It's even more spectacular, this image of the Eagle Nebula, so which is well popularized by the HST, beautiful HST images of this nebula. So, but you can see that this nebula, this pillar is broken. Actually, wherever there is a bright star, actually there is a empty space here. Looks like the pillar is broken. Actually, we are seeing the internal parts of the nebula in these infrared wavelengths.
So you can take, excuse me, sir. So you can take 15 minutes more. Is that okay?
Okay, sure. Okay, so this is a protostar. So this is a protostar where you can see the material that is ejected along a bipolar nebula. So I mean, each image I can talk many minutes describing this thing. What all these images tell us is the detail. The image is very sharp. A lot of structures are there. So we will study these structures and exactly show, we know the interaction of the stellar material with the surrounding medium. That gives us a lot of physics and chemistry of how things work at the astronomical scales. Well, this somewhat similar images, so I'll skip through that. So this, actually, this is one of the images which I am really thrilled about. For me, it's the greatest contribution of the JWST so far. So this is a Wolf-Rayet stars. Wolf-Rayet stars are really very massive stars. These are minimum like 30 times more mass than as compared to the sun. And in this image, what you're seeing is fresh places where the dust particles are formed. Usually, I mean, you need the formation of dust in the universe. Without the formation of dust, you can't form molecules, you can't form stars. So one of the fundamental problems of astrophysics is when exactly dust is formed. So that was in the textbook things. The time scale for dust formation was like a million years. So it is a slow process, and one of the fundamental problems is how you form dust in the universe, early universe. So this here is an example, a hostile ambience. Let's say this is a very hot star. The star is, I mean, the temperature of the star is more than 50,000 kelvins. And it has winds, powerful winds, which will blow everything away. And in this such a harsh condition, we are seeing the formation of dust over a period of less than 8 years. No, it's a human lifetime. So this, we know that this is a star in a binary system with another star, also a massive star. And both stars have heavy winds, but this Wolf-Rayet star has a heavier wind than the other star, and this winds collide. One star, I mean, wind from one star collides with the wind from other stars, and the zone of collision is the place where you can form dust. So nobody predicted, but here we are seeing the formation of dust, and the dust is formed exactly. These two stars are orbiting one another in a very elliptic orbit, and the the dust is formed only at the periastron passage of the massive star and the Wolf-Rayet. So only there for a short period of its orbit, the dust is formed, and after the dust is simply expelled into a larger distance. That's why it just moves outward, and after 8 years another plume of dust is formed and that moves. So that's why here there are like 17 rings of dust which are formed over the last 130 years, in our lifetime. So these are formed. So nobody expected this, and just it's a surprise image from the James Webb Space Telescope. So that's why I said it's one of the most thrilling image, just to know that in such a short lifetime, in question of few months, dust formation can happen. So, well, this is just a description of the orbits. This one massive star is orbiting this Wolf-Rayet stars, which has higher speed wind, so which bends the wind from the other star, and that's why this dust is formed. Okay, I'll quickly go through the planets, which is basically to illustrate that James Webb will discover a lot of things about the planetary atmospheres. So the technique used for that is the eclipsing technique, because the planets are too small and too faint to be resolved from the main stars. For example, if you see our planetary system, solar system, from another star, we won't be able to separate Earth or even Jupiter from the Sun. They will all seem together. Then how are we going to study the planets? So technique is, well, although we can't see, but we can, if we can measure very minute differences of light, so then we can, when a planet goes in front of the stellar disk, then we will see a lesser light. So this is what is shown here. So during the eclipse period, so we can see the effect of the light. And then what happens, if we are able to do the spectroscopy, we can detect elements, we can detect molecules. And because the star is passing in front of the planet is passing in front of the stars, so we can get the absorption features of whatever element, whatever molecules are there in the atmospheres of the planets. So that's the technique that have been used very successfully now with the James Webb Space Telescope. So, and I will skip through that. For example, in the Martian atmosphere, so we know that this is again taken with the James Webb Telescope. So we can see the different molecules, carbon dioxide, water molecules. We can see that Martian atmospheres have all these molecules, and we can now do the same kind of work for extraterrestrial planets. So all these molecules here, like hydrogen cyanide, methanol, formaldehyde, deuterated water, all these molecules we can detect in the spectra, because this telescope has the spectrographs mounted on that. So this is one of the examples, one of the systems called WASP 96b, so where water was detected, for example. And even more spectacular is the detection of, there's the same spectra. I'll go a little fast because I'm running behind time. So this is considered as the first detection of carbon dioxide outside the solar system, for example, in a planetary system. So carbon dioxide detected in this in this particular star called as WASP 39b. So this is the feature of the carbon monoxide. There is a lot of other interesting detection, like a ring around the Jupiter. So you can see a faint ring. Also, a lot of moons, all the moons of Neptune are directly seen using this space telescope. Okay, I will just go into the instruments. So next, so that just to highlight that the James Webb Space Telescope had to overcome a lot of challenges so that it could give all the results I quickly flashed for you. So one of the challenges is that the telescope has to be cooled, because a lot of radiation coming from the Earth itself or the telescope itself. So it has to shield against all these things. So it can be done using cooling. But the biggest problem is the sunlight. Sunlight heats the telescope, and without having a shield, you can't do anything. So a big shield is constructed, and transporting that shield is not at all silly. So the group found very novel ways of transporting the shield, metallic shields, very thin shields, but they can withstand all the solar light. And the telescope is always in the shadow, as we'll see soon. Telescope requires fuel for its existence, because it has to do the orbital corrections. So it will have a limited lifetime, not like HST, which is still going strong after 31 years. But this telescope was in the pre-launch said maybe 5 to 10 years of life it can have. But the telescope and the launch, everything became so perfect in this case that now they are very confident that the telescope will survive something like 26 years, or at least the propellant, what is left behind, which will last for these many years. No? So if some other problem is there, we may lose this telescope. Another problem is that the telescope is too far to do any servicing missions. So if any problem is there, it cannot be repaired, for example. No? So the telescope can stop working. So this is how the configuration is there. So it is in the what is called as L2, that is the second Lagrangian point. So that is to say it is always along the line of sight between Sun and the Earth. So always along the line of sight, it moves synchronously around the Sun and the Earth, and it is 4 times the distance of Moon, as is shown here in the bottom plot. So this distance is 4 times the distance of the Moon, and it is shielded. This is the solar shield, so it's shielded. So there's a lot of temperature difference. So it is around minus 233 Celsius is the temperature where the telescope is there. So it is cold, around 40 degree Kelvin temperature where you can detect very efficiently the infrared radiation. So this is another challenge for the Space Telescope. It's a 6.5 meter telescope. The HST was only 2.4 meter telescope. So it's a big telescope, and it cannot be made like from a single piece of the glass. So it has to be made lightweight and also multi-mirror, like what you see here, and it's all assembled there up. So that's another beauty of this telescope, that they could assemble everything up in the sky there, and everything worked to perfection. So here you can see the shield, sun shield. Sun is always the bottom here in this figure. And the instruments are all mounted in this cold region. So, and there are several instruments. So in the next few minutes I'll talk about the instruments. So, and usually when we think about a space telescope, we think about 1 or 2 instruments, mostly imaging instruments, giving fantastic images. But here, for the first time, a space telescope is carrying so many different complicated instruments. Even ground-based telescopes, as far as I know, there's no ground telescope that has at a time so many instruments available. No? So they change the instruments to have new instruments, but here, at a time, so many instruments are there. Any instrument can be selected there. And actually, there are several instruments that can be used simultaneously. So that's how it is designed. So these instruments broadly can be divided into the near-infrared imaging instruments, far-infrared imaging instruments, and near-infrared spectroscopy and far-infrared spectroscopy. So this is a broad categories, and in each one of them, it has so many other options. So that's what makes this JWST so special. No? So, for example, and all these instruments are mounted compactly, although each instrument has moving parts. So usually in a space telescope, moving parts are avoided, but this telescope has a lot of moving points, and still they move without interference with each other. So just to illustrate, don't bother about this values there, but just to illustrate the number of filters, it has around 50 filters of different widths, and that is also one of the reasons why we can get so many good images from this telescope, and good results. The spectrographs, these are the ones which take spectra to obtain the good values of redshifts, and it can be done in several varieties. It can be done just for one object, or every point in a particular image can be, we can get a spectra of that point. So this, and you can take image and later go, if you find something interesting, take a spectra. So everything can be done there itself. Earlier days, like with the HST, once something interesting there, then we go to a ground telescope and take spectra. No? So that takes time, and many times we can't do that. The ground telescope, that object is too faint, so that's why we can't do. No? So whereas here, because of the versatility of the instrument, so we can do in the same telescope many different kind of things. No? The last one is a time series. So, and it can take quick images or quick spectra, and this was required, for example, to study the planets, planetary atmospheres. So especially when it is going in the eclipse mode, so it lasts maybe 1 hour, the eclipse. So you need to sample several times, so to get the variation of different elements there. So you require a time series, and that's also available in this instrument. So that's why this is really the great planning by the engineers, the people, astronomers who planned it, and engineers who really made it work and to the perfections. No? So none of the instrument failed, and every option is available for use. No? So with this, I finish here just to point out some of the take-home points. So the James Webb Space Telescope has already surpassed the expectations. So although one did all these things, one was a skeptic with so much complicities. Will it work? The good news is that it has worked to perfection. The pointing of the telescope is very good, and that makes the image quality also more than what was expected from the ground-based observations when it was in the laboratory. So it is very efficient, which means the mirror is very clean, and it has not been contaminated during its transport, let's say. And for all this, and lifetime is much more than expected. It's because of the perfect launch. You know? So, and well, astronomers, including me, are overwhelmed by its success. No? So, and we are in for exciting discoveries in the coming decades. You know? So, it's earlier we thought it would work only for 5 years. Now, its lifetime has been increased by 5 times. So, I think with that, I will end, and I'll be happy to accept any questions that you may have. Thank you.
Thank you, Dr. Divakar Mayya. Now I call upon Dr. Kiran Kolankar to handle question and answer sessions.
Yes, thank you. Thank you for such a nice lecture. There is one, start with one general question which is there in chat box. We didn't take it up that time because it was not specific to the talk. So can we detect dark matter, or is it just a theory, or it is real? That is a question.
Yeah. So in the beginning, I said that is one topic that this James Webb will not be able to directly address. We don't know, but at least that is not one of the frontier fields that it will be aiming to resolve.
Okay. Mr. Anchal Sita Prasad, can you ask your question? Or type in the chat box. Dr. Anchal Sita Prasad. Okay, maybe by the